Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. We'll talk about Introduction to Distribution Network Load Flow and Sparsity Quantification. Now, let us understand what are the challenges in distribution network load flows. Now, first of all, the challenges associated with distribution load flow because the distribution networks are mostly radial in their structure and it possesses a high value of R by X, and the unbalanced loads become a common factor, and there are mutual impedance effect and large number of buses in the network. So, what we like to highlight here, unlike meshed transmission networks, distribution systems are mostly radial, and because of which it requires a specialized load flow technique instead of a conventional Gauss-Seidel or Newton-Raphson. Now, distribution networks, as we have seen in our previous lectures, do possess actually high R by X ratio, and the high resistance to reactance ratio in distribution lines affect convergence using Newton-Raphson or fast decoupled methods. Many distribution systems have single phase and two phase loads, making the conventional three phase method ineffective because it is purely unbalanced. Presence of mutual coupling in untransposed multi-phase lines complicates the power flow calculations. Distribution systems have many buses, increasing computational complexity and requiring efficient numerical techniques to solve load flow analysis. Now, distribution network load flow methods are majorly of two types. One is backward forward sweep, which is very commonly used in the past, and the second one is direct load flow approach. Let us try to understand what is backward forward sweep method for distribution systems. Now, backward sweep means at iteration k, starting from the branches in the last layer and moving towards the branches connected to the root node network, the current in branch I is calculated as II is the current injection at that node plus the summation of currents in branch spreading out from this node. Now, in case of forward sweep, nodal voltages are updated in a forward sweep starting from branches in the first layer towards those in the last. For each branch, let us say 3, the voltage at node 4 is calculated using updated voltage at node 2 and branch current calculated in the preceding backward sweep. That means whatever the current being calculated is being used to calculate the voltages. So, the V4 will be V2 minus Z3 into II. So, if I am interested to know what is the value of my voltage at bus number 4, which is nothing but the voltage at bus number 2 minus the impedance, the drop in the line branch number 3, that is so called II into Z3. Here Z3 is the series impedance of the branch number 3. Now, the drawbacks of forward and backward sweep method, because it is not so simple, though it is simple to solve, but most of the time it poses challenges, not applicable to mesh networks because it is only applicable to radiality. If it is meshed or weakly meshed or ring type networks, then backward forward sweep load flows for distribution system is no more applicable. Now, it struggles with bidirectional power flow induced by DERs leading to convergence issues. High DR penetration can result in poor convergence or instability. Nonlinear voltage dependent loads make FBS iterations less reliable. It is a static method that does not capture dynamism, real-time variation in DR outputs. Inverter-based DR are not accurately modeled by the simplified backward-forward search approach. So, what are the issues here? The backward-forward distribution load flow algorithm is no more applicable for the network which are meshed or weakly meshed, and which is also not suitable for a system which is active, where lot of renewable generations and distributed energy resources are connected. Now, try to understand what is direct load flow method. The power injections can be converted to the equivalent current injection And the relationship between the bus current injection and branch current can be expressed as B matrix, which is BIBC multiplied by the I matrix, and BIBC is known as bus injection to branch current matrix. The bus voltage can be expressed as a function of branch currents, line parameters, and the substation voltages. Therefore, the relationship between branch current and bus voltages can be expressed as delta V, which is BCBV matrix multiplied by the B matrix. BCBV is nothing but branch current to bus voltage matrix. The relationship between bus current injection and bus voltage now can be calculated as delta V. We can substitute the value of B, which is from the equation number 16.3, which is B equal to BIBC multiplied by I matrix. So, if you substitute the value of B from equation number 16.3, the 16.4 equation becomes delta V, which is BCBV BIBC multiplied by the I matrix. Now, there are a bit of limitations. Now, steady state nature of direct load flow does not capture rapid dynamic variations inherent with DR outputs. This also poses the same challenge not to accommodate DR integrations easily. Inflexibility in adapting to continuous changes in DR generation may require frequent matrix recalculations. Simplified modeling may not accurately represent sophisticated power electronics or inverter behaviors. Now, in case of distribution load flow with DRs, there are many challenges one can pose, because as of now what we have discussed is a simple distribution load flow algorithm having loads and generation at substation. However, the moment we integrate distributed energy resources, then bidirectional power flow due to DR challenges traditional unidirectional flow assumptions. Normally, we assume the power is flowing from the main bus towards the load bus, which is not true in case of a DR integration system. So, now what is happening? We have the main grid, then we have distribution substation, and this distribution substation is not only catering loads, but it is also connected to solar energy, battery storage, electric vehicles and winds, and moreover there could be few industrial loads also. Now, voltage fluctuations from intermittent DRs can lead to overvoltage or undervoltage issues. Uncertainty in DR output makes accurate load flow modeling quite difficult. Rapid variations in generation and load requires dynamic and adaptive load flow solutions. Increased nonlinearity in system behavior complicates convergence of traditional methods. Impact of DRs is highly dependent on the location within the network. And hence, what many authors have recommended, looking at the complexity, we proposed a graphical load flow analysis for DR integrated distribution networks, and I hope I will be able to understand and appreciate, and probably you can also attempt to solve a very simple problem using graphical load flow analysis of DRs. Now, in case of graphical load flow for DR integrated distribution network, which uses connectivity and bus branch topology matrix to capture the network's graphical structure, maintains matrix sizes similar to single phase equivalent, preserving inherent sparsity, avoids direct matrix multiplication, ensuring computational efficiency and with complex DR integration. So, it majorly avoids the classical approach of multiplication and inversion in case of graphical load flow solutions, efficiently handles diverse components, that is unbalanced loads, regulators, different load configurations, PV based DRs, and a wide range of R by X ratios. Graphical load flow analysis also demonstrates robustness and efficiency through extensive test analysis compared to contemporary approaches. Now, let us try to understand what are the advantages of using load flow analysis of DR integrated distribution networks. Graph based power flow algorithm that forms two sets of matrices. The first one is popularly known as connectivity matrices, which captures the network configuration And then the second one is bus branch topology matrix, which computes the load flow parameters such as load current beyond branch, branch current, voltage drop, and voltage matrices. A specialized sensitivity matrix is developed to model PV buses, active power and voltage specified, distributed generators, enabling calculation of necessary reactive injection to compensate voltage deviation at each and every bus. The method is robust and computationally efficient, handling various load models and a wide range of R by X ratios while reducing matrix size and sparsity issues compared to contemporary or classical approaches. Now, slowly try to understand what is graphical load flow approach. Now, we can just first of all try to have a 5-bus system. This is my bus number 1, 2, 3, 4 and 5, and they are all connected, radially connected, and this is known as branch 1, branch 2, branch 3, branch 4. Now, graphical load flow refers to a power flow analysis method that uses graph theory concept to model and solve the distribution network's load flow problem. Based on graph theory, it models the power system as a graph where buses are nodes and branches are edges, enabling efficient network representation as shown in the figure 16.4. Now, matrix representation uses matrices like connectivity and topology matrices derived from the graph structure to compute power flow without complex sequential calculations. Now, efficient for sparse network because especially suited for radial and weakly meshed distribution systems where the network is sparse and graph-based techniques simplify the whole computation of the process. Enhanced computational speed because graph-based method eliminates the need for direct matrix multiplication and reduce memory usages, making the whole process faster and more scalable than the traditional approaches. Now, every bus is connected to the source bus through a unique branch set called path branch set, that is PBS. Now, what we wanted to highlight here, if you have a system or a network having 5 buses, 1, 2, 3, 4, 5, branch numbering 1, 2, 3, 4, and we can simply say the blue line, it is the source bus to the bus 3, and the red line is the source bus to bus 5. Okay, so this is you could see the red lines as well as blue lines. Now, let us calculate what is the path branch set PBS for bus number 3. If I am interested to calculate this one, so this is nothing but basically the set is going to be branch 1 and branch 2. So, basically from the source how we are going to reach to this point 3. Okay. Similarly, when I calculate for bus 5, it is going to be 1, 3 and 4. This is going to be 1, 3 and 4. So, PBS, that is every bus which has been connected between source bus through a unique branch set which is known as my PBS. For bus number 3, it is going to be 1 and 2, and for bus number 5, it is going to be 1, 3 and 4. Now, what are the matrices that we normally use for graphical methods? The following matrices are to be constructed to perform a graphical load flow. The first one is going to be connectivity matrix. We will discuss how these matrices are generated, represented by E, weighted connectivity matrix represented by W, bus branch topology matrix represented by T, load current beyond branch matrix represented by F, branch current matrix represented by J, voltage matrix represented by D, source to other bus drop matrix represented by L. Now, we will just slowly get into what is connectivity matrix E. Now, this connectivity matrix defines the connectivity from source bus to end bus of radial distribution network with total of m and n number of branches and buses respectively. That means the connectivity matrix Eij is equal to 1 if branch j belongs to phi I, because you know what is phi I, and it is equal to 0 if the branch j is not belongs to phi I. Once again I repeat, the connectivity matrix element Eij equal to 1 if branch j belongs to the phi I. What is phi I? For an example, if belongs to this set 1 and 2, then it is 1. If not, then we call it is 0. That is Eij, either it will be 1 or 0, where I is basically 1, 2 up to gamma, and j belongs to 1, 2 up to m, and gamma is the total number of PV buses with distributed generations, and m is the total number of branches in the distribution networks. And this is the same network we are using for our case study. Now let us understand what is weighted connectivity matrix W. The matrix provides the connectivity of path from slack node to the leaf node. The existence of impedance in each path can be introduced using weighted connectivity matrix W of the order gamma cross M. The weighted connectivity matrix Wij is given by Eij, which has already been calculated, multiplied by Zj, and Zj is nothing but simply the impedance of the branch. Let us move to bus branch topology matrix T. This matrix defines the topology of the distribution system and depicts buses comes beyond each branch in the radial distribution system. This matrix is formulated using a searching technique on source to leaf connectivity matrix of the distribution system. Now Tij, which is either equal to 1 or 0, it is 1 if jth bus exists beyond branch I, it is 0 if jth bus does not exist beyond branch I, where I varies from actually 1 to m and j varies from actually 1 to n. We can slowly move to load current beyond branch matrix F. This matrix stores the load current existing beyond each branch in the network, and suitable operations on it will provide current flowing through each branch. The load current computation procedure is not uniform throughout the network since there are varieties of loads. This matrix computation depends upon bus branch topology matrix and load current computation. We will now slowly get into load current beyond branch matrix F, and that F, the load current beyond branch matrix F, can be expressed through equation number 16.9, and you could see Fij is nothing but my Tij multiplied by Sj upon Vj, which is equal to Tij multiplied by Ij. And as you all know, Vj is the complex voltage of the bus J, Ij is the complex load current at bus J, Sj is the complex power at bus J, and Ti is the element of bus branch topology matrix. Branch current matrix J is the load current beyond branch matrix helps to compute the load current, and suitable operation on it will provide current following through each branch. So Ji is defined as summation of j equal to 1 to n Fij. So we have determined Fij, we have to sum it up from bus number 1 to the nth bus. So Ji is the current flowing through each branch j. Then voltage matrix D, this matrix provides the voltage drop in branches existing in the path connecting slack bus to leaf bus. Drop due to impedance can be represented by Dij, which is equal to Wij into Ji. The matrix reveals the drop from source to leaf node due to impedance offered to branch current flow existing in each path. Source to other bus drop matrix L, which is a very interesting matrix. This matrix provides the voltage drop in each of all the branches existing in the path connecting slack buses to other buses in the respective path due to presence of self and mutual coupling impedances of the branches. Drop due to impedance can be represented by Lij, which is summation of j equal to 1 to m Dij. If Eij equal to 1, it is equal to 0 if Eij equal to 0. Now, then we move slowly to bus voltage computation. The computation of bus voltage for each phase depends upon two significant matrices formulated for the distribution system: source to other bus drop matrix and source to leaf connectivity matrix. A search operation is performed on the mathematical operational resultant of source to other bus drop matrix and source to leaf connectivity matrix for selecting the maximum value from each column of the formulated matrix as per the following equations. Now, Vi is defined as maximum of 1 angle 0 times EI1 minus LI1 or 1 angle 0 EI2 minus LI2 up to the last gamma point, and you to identify the maximum out of which will be my B of I. With this understanding of different matrices, we stop our today's lecture. However, in the next lecture, we will try to understand how these matrices are being used and applied for obtaining the voltage solution of a distribution system, which is not only radial, but also a complicated radial cum mesh networks integrated with distributed energy resources. Thank you.